Hi, in this video, I will be showing you problem number 1 of chapter 15, section 1. Estimate the volume of the solid that lies below the surface z equal to xy and above the rectangle R, which consists of all the points x, y, 0 less than or equal to x less than or equal to 6, and 0 less than or equal to y less than or equal to 4. Use a Riemann sum with m equal to 3 and n equal to 2 and take the sample point to be the upper right corner of each square. Use part B, use the midpoint rule to estimate the volume of the solid in part A. Let's underline the keywords. So volume is what we are finding. So it's a double integral process. Surface is z equal to xy. And then we are going to divide the x-axis with m equal to 3 subintervals, and the y-axis with n equal to 4, which is 2 subintervals, and take the sample point to the upper right corner of each square for part A. And for part B, we are going to estimate the volume using midpoint rule. Instead of any sample point, the sample point has to be the midpoint in the second case. So let's revisit the formulas or what we mean by a double integral with the help of Riemann sum. We'll explain that first, which we learned in class. Write the definition of double integral over R f of xy dA as a limit. So double integral over R here means a rectangle. F of xy dA is limit as m and n approaching infinity, sigma I varying from 1 to m and sigma I j varying from 1 to n, f of xij star, yij star, delta A. Xij star, yij star stands for the sample point in the rectangle Rij, and delta A is the area of that rectangle Rij. So here, something about the Riemann sum. Riemann sum is, I call it big S. Big S denotes double integral here. So it's an infinite sum. Infinite sum becomes an elongated S, which is double integral. We have done the same thing in Calculus 1 single variable class, where we do integral of f of x dx, which is area under the graph of the function, as a Riemann sum. So it is limit sigma I varying from 1 through n, and n approaching infinity, f of xi delta x. So here it is height times width. That will become the area of a rectangle. So we are going to divide the integral from 0 to the interval from 0 to a or a through b into number of subintervals, say n, and then we allow n to approach infinity. So the area was approximated by rectangles. Then sum of all the rectangles areas will become the area under the graph of the function. This was about single variable integral, the meaning of the integral. Same thing here, the double integral, because we are multiplying the height with the area, this becomes the volume. So infinite approximation becomes double integral, the volume of this volume under the surface about the domain. Same thing can be done with the help of a midpoint. Here we use any sample point here in the interval, in the rectangle Rij, but we can use the midpoint also. What is the midpoint rule? What is the midpoint rule? What is the midpoint rule for double integrals say? The midpoint rule for double integral says that we approximate the double integral over R f of x y dA by the double Riemann sum, kind of similar to the above. Limit is m and n approaching infinity, sigma I varying from 1 to m times sigma j varying from 1 to n f of xi bar yj bar delta A, where xi bar yj bar are the centers of the subrectangles. So that is what the midpoint rule is. We'll see how these two are applied for our problem, where z equal to xy or f of xy equal to x times y. So given z equal to xy or f of x comma y equal to xy, and the region R is all those xy's is that 0 less than or equal to x less than or equal to 6, and y lies between 0 and 4. We are given m equal to 3 and n equal to 2, or in other words, number of subintervals on the x-axis is 3, the number of subintervals on the y-axis is 2. So that way we get 6 subrectangles. M equal to 3 denotes the number of subintervals on the x-axis is 3. And n equal to 2 denotes the number of intervals along the y-axis. So delta x is the length of each subinterval along the x-axis, which is b minus a over m, which is 6 minus 0 over 3, which is equal to 2. And delta y is 4 minus 0 over 2, which is equal to 2. So if we picturize this along the x and y, so x runs from 0 to 6, y runs from 0 to 4. So we get a rectangle, but along the x we have to divide into 3 subintervals, each of width 2. Along the y we have to divide into 2 subintervals, each of width 2. So we'll divide that. So we get 6 subrectangles. For the first part we have to use a right endpoint of each square. Then the subrectangles are shown in this figure. Each subrectangle or subsquare is of area 2 times 2, 4. Each square Rij is of area delta A, which is equal to 4. Now, volume of the surface above this rectangle is V approximately equal to I varying from 1 to 3, sigma I varying from 1 to 3, sigma j varying from 1 to 2, f of xij, yij, the right end points of each subrectangle, right corner, right top corner, f of xij, xi, yj, delta A. Choosing the sample points as right corner of the rectangle, right top corner of the rectangles, we get V is approximately equal to f2, 2 delta A plus f2, 4 delta A. Then we have to choose this point, which is f of 4, 2. So f of 4, 2 delta A plus f of 4, 4 delta A, which is this point, plus f of 6, 2 delta A plus f of 6, 4 delta A. Delta A is common, which is equal to 4. We just stated that. So computing these values from the equation f of xy equal to x times y. So we are multiplying the x coordinate with the y coordinate for each value, f of 2, 2, f of 2, 4, etc. We get v is approximately equal to 4 times 4 plus 8 times 4 plus 8 times 4 plus 16 times 4 plus 12 times 4 plus 24 times 4. If you simplify, this is going to be equal to 288. So with the help of top right corner sample points, we get the volume approximately equal to 288. For the second part, we have to choose the midpoint from each sub-rectangle. V is approximately equal to sigma I varying from 1 to 3, sigma j varying from 1 to 2, f of xi bar, comma yj bar delta A, where xi bar, yj bar are the midpoints or you can say centers of the rectangles or centers of the squares. So V is approximately equal to f of 1, 1, f of 1, 3 plus f of 3, 1 plus f of 3, 3 plus f of 5, 1 plus f of 5, 3 all multiplied by delta A, which is equal to 4. If we compute these values and we get 1 plus 3 plus 3 plus 9 plus 5 plus 15 all multiplied by 4. This will be equal to 144. So if we use the midpoint, the volume equal to 144. Use the top right corner, the volume is 288. So keep in mind, when we do this Riemann sum, what we actually evaluate is the volume under the surface above the region, or if all the surface, all of the equation, all the surface, the entire part of the surface is above the x-axis. In case a part of the surface is below and part of the surface is above, then we have to do V1 minus V2, where V sub 1 denotes a volume under the surface above the domain, and V2 is above the surface below the domain. We are going to subtract these two, which is called the net volume. Okay, so be aware of that, and we will do a problem of iterated integral, or how to find out the double integral over a rectangle in the next video. Hope this video helps.